So today we're going to be talking again about how to compute the derivative of the negative likelihood loss function with respect to this weight matrix here for problem 2D on this 6036P set. So to do that, I'm going to just draw a little diagram here. And what we're trying to compute is the gradient of this NLL loss function, right? And so this NLL loss function directly depends, this NLL loss right here, depends directly on these AJ values. So this, I'll use a different color, depends on these AJ values, A1, A2, all the way to ANL. And so, but these I1, A2, ANL, all of these AJs can be calculated using this softmax function. So AJ depends on these ZJs. So let me draw that right here. So all these A values can be computed from these ZJ values. So I'm just going to draw one here, ZJ. So our first task in backpropagation is going to be to compute the derivative of this NLL loss with respect to ZJ. So we can write this as the derivative of NLL with respect to ZJ. And how do we do this? We use the multivariable chain rule. And the multivariable chain rule is given by this sum from j or I equals 1 to NL of, first we have the derivative, let me use a different color. First we have the derivative of NLL with respect to AI. And then we also then have the derivative of AI with respect to ZJ. So this is the first step, and this allows us to compute the derivative of the NLL loss function with respect to ZJ, which are these pre-activations. So then we have another challenge, which is, okay, these ZJs are not, we don't want the derivative with respect to ZJ, we want the derivative with respect to these weights. So let's draw another diagram here. So we have NLL. And so this NLL depends on these ZJs indirectly through these A's, but we can treat it as though they depend directly. So let's write these ZJs, Z1, Z2, Z, and L. So we can draw it like this. And then we have these ZJs, then one particular value of the weight vector. So let's say WLM. All of these ZJs could, in theory, depend on WLM. So we can write out the multivariable chain rule again, and we have the derivative of NLL with respect to WLM is equal to the sum, and let's use like a different dummy index here. D equals 1 to NL of, first we have the derivative NLL with respect to zj. And then secondly, we have the derivative. Sorry, I used the wrong index here. Let me erase this here. So sorry, let me just derivative with respect to z. Now this is zd, and then times the derivative of z derivative of z d with respect to w l m. So these are the two multivariable chain rule expressions that we need to solve this problem. And you'll wonder, why do we have this sum? The reason is that each one of these expressions is the derivative along one of these chains. And so to compute the full effect, we add up the contributions from each one of these chains, similarly here. Okay, so now that we have this, I will scroll down. Okay, so now I want to compute this derivative. So first we're going to start out with this derivative here, right here. Actually, this one right here. Okay, so the derivative of the NLL with respect to AI, what is this? Now let's recall what the definition of the NLL loss function is. So right here we have NLL is equal to the negative sum of yj times log of aj. So let's write that out. So this is going to be the derivative with respect to AI of negative sum from I equals 1, or from j equals 1 to NL of yj log of aj. Okay, so how do we compute this? The derivative goes inside the sum, so we can write negative sum j equals 1 to NL, and then the yj is just a constant. Now, similarly, we can, for this natural log of aj, we can use the chain rule. So it's going to be 1 over aj, that's the derivative of ln aj with respect to aj, times the derivative of aj with respect to ai. That is just using the chain rule. We have this outer variable and then this inner variable. So we take first the outer function with respect to the outer variable, and then the outer variable with respect to the inner variable. So what is this derivative here? What is this? Well, this derivative is going to be equal to 1 when I equals j. You're just taking the derivative of function x with respect to itself, so it's going to equal 1, but it's going to be equal to 0 when I is not equal to j. And this function has a very special name. This function is called the Kronecker delta, delta ij. This is how it's defined. It is 1 when I equal to j, and 0 when I is not equal to j. So we can write that. We can write negative sum over j, yj over aj times delta ij. Now you'll notice that this delta ij is 0 most of the time. So most of the terms of this sum are going to be 0. There is, however, one and exactly one term in the sum that is not equal to 0, and that is the term where j happens to be equal to the particular value of I. So that means that we can get rid of this sum and set j equals I. So we're going to do that. And so that means that this sum evaluates to negative yi over ai. So this is the answer. The derivative of NLL with respect to ai is negative y over ai. Okay, so in this video we'll probably just do this derivative, and then we'll save the next one for the next video. So we'll do this derivative. And this derivative is somewhat complicated. And the reason is that if we recall, aj is this complicated softmax function. So the derivative, we're going to have to use the quotient rule and some fancy index tricks. So let's go down here, get some more real estate. And we'll rewrite this. We know that aj equals, let me make sure I'm getting my indices right. So we want ai. Okay, yes, ai. So let me go back. So we want ai is equal to e to the zi over the sum from, we'll use a dummy variable, p equals 1 to nl of e to the zp. So this is, just written what is up there in just a slightly different form. So we want to compute the derivative of ai with respect to zj. Okay, so this is the derivative with respect to zj of this, e to the zi over sum p e to the zp. Okay, and so how do we do this? Well, we use the quotient rule. So that means we do the derivative of the top, or the bottom function times the derivative of the top. So bottom function times derivative of the top. Now the derivative of e to the zi is just e to the zi times the derivative of zi with respect to zj, right? It's just the chain rule again. Now we subtract off the top function times the derivative of the bottom function. So derivative with respect to zj of sum p equals 1 to nl e to the zp. Of course, we divide everything by the bottom function squared. So we have sum over p e to the zp squared. Okay, so let us simplify this. Again, we have a derivative of zi with respect to zj. We can simplify this using the Kronecker delta. So let's rewrite this. Sum over p, e to the zp. And so this is e to the zi times delta ij, and then minus e to the zi. Now again, we can write this as sum over p, and then this derivative is very similar to the one we just did earlier. This is going to be e to the zp times, now it's going to be derivative zp with respect to zj, but this is just delta pj, and then over sum p e to the zp squared. Okay, one final simplification to make, or actually a couple simplifications to make. We can kill this sum because this over this sum, this p, this delta pj is only non-zero when p equals j. So there's only going to be one positive term in this sum. This, however, there's no sum here, so we just leave that as is. So we have sum e to the zi delta ij, and then minus, this kills the sum and sets p equal to j, minus e to the zi e to the zj over sum over p e to the zp squared. Okay, now one thing we'll notice, we're going to break this up into two. Okay, so let's go down here. This is equal to, we can break this up into two terms, and in the first term we're going to write this as e to the zi over sum p e to the zp. Notice how the numerator and denominator cancels for this term, delta ij. And then on the other one, we're going to write this as e to the zi over sum p e to the zp, and then times e to the zj over sum p cp. Okay, now when we notice, this is the definition of the softmax function, ai. They're completely identical. Same here. So we can rewrite this as ai delta ij minus ai, and this is the same thing except with the index j here. So this is aj. Can factor out the ai and write this as ai times delta ij minus aj. And this, my friends, is the answer. All right, that is long enough for this video, so I will see you next video.